So, good morning, everyone. Welcome to the fifth and final session of Introduction to Fortran. And today we will talk more about performance, and we have an icebreaker questions for you. According to you, which is the fastest programming language? Please give your answer there. We use the same collaborative document as the previous four events, where you can ask questions and give answers. Which is the collaborative document has links to all the previous sessions videos, as well as the archived questions and the demo course for from all the events. And two important things before I give this to Ole is one, we are recording this event, and so please feel free to switch off your camera if you haven't done it already. But we will be editing the videos anyway. And the second is we follow the code of conduct. It's like having a friendly atmosphere and being respectful to each other, and both participants and instructors follow the code of conduct. That is all from my side to give you the logistics, and without much delay, I will give it to Ole, who is your instructor. Ole, to you.
Thank you. Thank you. We'll get right on with it. Yeah, two people answer C, which is an interesting one, because if you know how to program, the answer is probably right. If you don't really know how to program and use pointers and pointers to pointer and a lot of the other stuff, C is very bad. Fortran has the advantage of preventing you from doing silly mistakes of that kind, because the language doesn't support it. So if you know how to program, C is an excellent language. If you don't know how to program, it's very easy to write code that is not efficient. So if you stick to array operations and such, and do aliasing, turn off aliasing and so on, they are comparable. They both generate very, very fast code. Of course, if you go into things like, I had planned to show this later on, but we can show it straight away. Here we have a function that I wrote to measure time. You see, it's a struct time spec clock get time, and it's a nanosecond resolution. This is typically where C# doing this in Fortran would be impossible. So there is no news that C and Fortran go hand in hand, goes together for many years, for decades back, where you use C for tasks like this, reading time, etc., and then Fortran for the higher level stuff. No coincidence that the Linux kernel is written in C. So for anything that has to do with sysadmin or deeper stuff like operating system things like reading the clock and so on, returning sensible value, C is absolutely the way to go. Anyway, we'll start with today's topic. It's mostly about performance. Performance. If your program finishes in a couple of seconds, it doesn't really matter if it takes 2 seconds or a half a second or 10 seconds. You get an answer more or less in real time. But if your program runs for a week or more, it could be quite nice if you get the answer in overnight instead of running for a week. So hence, performance is important. This we've seen before. You can say, performance, do I care? Which I just said, I care if it takes a long time. If the program finishes in a few seconds, I don't care. I mean, a Python script, Python program that do some data in extractions, etc., and finish in a couple of seconds, I don't care. I mean, it doesn't matter. But if you run for a very long time, it does really care, even a few percent amount of days or hours. So, an answer next week or today, it's the relevant question to ask. Where do I put in all my effort? I thought of making it very, very simple. this time so that we could have time to actually run the examples. I took matrix multiplication, which is things that the computer does a lot, is a well-known thing, and all machine learning actually relies on matrix multiplication. So it's matrix multiplication over and over and over again, and for many operations in linear algebra, it boils down to memory, to matrix multiplication. It's a well-known thing, and computers does a lot of linear algebra, and when it's not doing linear algebra, it's doing Fourier transforms. But Fourier transform is a bit more tricky than matrix multiplication. So, and then also with the matrix multiplication is that 3 nested do loops, which is also prevalent in weather code. So stepping through either lat long and altitude or lat long and time or all the 4 of them, then it's comparable to that, and it can serve as a proxy for your code, for which there is generally no library. Of course, if you can use a library, you're good to go. If you can do it, then you can even do matrix multiplication in Python and get the same result, same speed as you get in any other language. But if you have to write the code yourself, then you're stuck because there is no library. Then you have to use a high performance language. So this is the task for today. 3 nested do loops. Fortran is column major, so the first index is the column and should be the one that runs the innermost loop, which is the I loop, and the I is the first index. We have a test for that you can run yourself. Yeah. So I will come back to how the data is stored. I mean, A and J here and A and J there are the same, and the I here, but you see the J and L are different, and then L and J here. So this we already see could pose problems when it comes to the caches and so on. Since today's computers are based on cache, they are not real supercomputers. A real supercomputer in the old days had memory system that could keep up with the CPU, but that is long gone. Today we have to rely on caching, and that poses yet another part of a layer of complexity. So I'll prepare some different files that you can find in the here in the introduction to Fortran workshop day 5, MXM. The 1 and 2 are the first that we will continue with. I normally use 4000 as the range. If you give it a too large range, it will run out of memory. Hopefully C group and or Slurm will prevent you from taking down the node. But we'll see. So we can actually start looking on the code. There is an issue with the reservation, so we'll cover that when needed. Is the size big enough? Or you want bigger characters, bigger font?
Would be nice to have a little bit bigger.
Okay.
I'm using my laptop screen.
I have a large screen here. We go to try one more.
Okay,
Better?
Yeah.
Now yep. A simple program. I will not use the GCC. I will go straight for the Intel compiler, or it doesn't really matter. We can try with C, with GCC. And I check for the command line argument. I don't think we've covered that one before. And if that's the less than 1, I just print out a message that how to use it, and then call exit 2. 2 is for misuse. The exit code is for misuse. Then if you give an argument, I try to read it as an integer. I read it from the buffer, the arg buffer, so it's an internal file. if that went okay, if you don't bail out, if you give characters instead of numbers, it crashes. So that's okay. And because, yeah, we could have tested for sensible input, but that we covered before. We allocate the arrays. And since we are, as you could remember, we said elements in matrix C equal to the same element as before in C. So it's essential that all elements of the matrix C is allocated with 0, initialized with 0. So in the allocation statement, I put in source 00 of type real 64, since the array A, B, and C are of type real 64, double precision or whatever you like to call it. Again, the beauty of the vector syntax in Fortran, you just say call random number, giving it a matrix as an input. All elements will be set to different random numbers. Same with B. I start the timer, which is covered in here. I wrote a module, timings. It has an interface to an external function, myseconds, that I showed you before. And here we can see that there is ISO binding built into the Fortran language. And unfortunately, C is a bit more sloppy with the typing. So C underscore double is C double, and normally C double is 64-bit. But you cannot really be 100% sure that it always is backwards and forwards in time. So if you get an old program or a new program in the future, read a little bit before you rely that C double is 64-bit. It normally is, so it's easy to make that assumption. We set the function, and then in this module, you see up here, outside of the subroutines, I declare two variables, start time and end time. So the subroutine uses the start time and the end time. So if we were using Julia, we had needed to they tightened up. So we would have to say global before this, but we don't need that in Fortran. So we just use start time, which is a global variable, and then end time. And then we have some show results where we first calculate the number of operations. That's n to the power of 3 operations in the matrix multiplication. We calculate the footprint of the 3 matrices. And we print out some numbers of the total footprint, the wall time, the operations I'm commented out, and how many gigaflops per second. So that's this module is used the whole of today, the whole day. So we call start timer, we do the matrix multiplication, we stop the timer, and we print out the results. And I print out some sums down here so that you can see sum of C, which is summing up all the elements of the matrix C. And again, the beauty of a sum function, it takes any kind of structure. And if we want to test, I say module list. We can take the Intel Fortran compiler. We could also test the different compilers, but let's start with the Intel compiler. Module load. ML is a shorthand for module load. So you can say module load. Yep. Now we have access to iFort 21.9 version. We can say this is you can say iFort help, which prints out a very long list of options. That one you can redirect to a file, which I already have. Should have, yeah. And I also think I copied it to the directory, or you can just forward and print it out. Here is all the optimization things that you'll need. if you want to dig deeper in, you have to use the web interface and read. In addition to all of this, I prepared a makefile. I know that it's been request for teaching a training for how to make a makefile. So this is not a training, it's just a makefile to make life easier for us today, but it's a very simple makefile. So you can use this as a template and start reading this makefile to understand what's going on. It's a bit sensitive for spaces and tabs and so on, so be careful with that. I set the compiler, I set the C compiler to GCC. GCC is always present, so, and it's only millisecond that it's compiled with GCC. Here I set the iFort, which is the Intel Fortran. Targets are MKM1 through 6, and there are two different of number 6, and there is one for library and one for profile. And the dependency files are here, timings, o.object, timings. I should actually have said timings F90, but it doesn't matter. Then timing mod and millisecond. So these files, if they are not there, they will be called into existence here. Timings O and timings mod depends on timings F90. They are built with this, and millisecond O, if not the object file doesn't exist, is built like this. Then there is the clean statement, which you should run. And you should use the phony line, because if not, if you make a file called clean, the make file will think, oh, the clean file exists, so I don't have to make it, and then it won't run this file. But now I override that by setting a phony argument called clean. So make clean should clean up all junk. Now it's make MXM1 timings millisecond. Then we now have an executable called mx1.x, and I generally give it 4000. So now we are actually multiplying a matrix of 4000. So I hope that most of you have managed to get into Saga and could try this.
Ole, I have some news for the reservation.
Yeah.
We forget to add a partition Excel.
Ah, right. I'll attend to that right away.
Yeah.
Aha. Partition accelerate, yeah. Is it accel or accelerate? I think it does accel. We'll try.
Excel, I was muted, sorry. Actually, this font is small for me. I'm not sure.
Yeah,
how
I
this-
know it, just to show that this is the correct way. I'm going to be nice today. I'm going to take this file. Put it in here. Like this, and then I'm going to copy the file to cluster project NN 997 introduction day 5, like this. Now it should be possible to run this one. and get access to the C1 and C2 nodes, C7 1 and 2. It's only me that logged in on C1. But going back to the matrix multiplication, at the 4000 by 4000 matrix, it has a footprint of 366 megabyte. It took 41 seconds to complete, and we got 1.5 gigaflops per second, which is slightly less or far less than you have the theoretical maximum. But that was run, yeah. That's an interesting thing in itself, but we'll continue with our quest for higher performance. But there is another interesting thing going on. But we'll just wait and see if some more people have managed to log in and run yourself, or do you want me just to run all the examples and then you just follow? We should have time to let users run the examples themselves, but if not, then
Should we give 5 minutes to
yeah,
run it?
we can easily give 5 minutes.
Yeah, exercise time.
But it's a bit important that you note down the performance we got from the first MX1, which is 1.5 gigaflops per second. Because, or write down what you get yourself. Because the next,
Yeah, Ole, there was some something on the collaborative document about NV Fortran error. Number 2.
yeah. Right. That is that you need to change the makefile here. Sorry for that. The makefile, you can set the Fortran compiler to start here. And then if you didn't have selected iFort as the Fortran compiler, you get that. If you get NV Fortran instead of iFort, of course it won't work because we haven't loaded the NVIDIA ecosystem of compilers. So you need to edit the makefile and make sure that the FC, the Fortran compiler, is set to iFort. Of course, I could make it easy. I could say CP makefile. Like this, and then it should be okay. Copy it. But it's an interesting error, and it's also an exercise to make sure that the makefile suit your needs. Because if you get the makefile from somewhere, it generally specified CC and FC to the compiler, and then it says capital CXX for C++. So be warned that the makefile might not be set up correctly when you receive a makefile from somewhere. So did anyone manage to get it running and get some answers?
We ask a poll.
No, if they need more time, they probably could ask for more time, but
Yeah, then I think we can continue.
yeah, we can continue. The next demo or exercise are more or less identical, except I swapped the indexes here. Now I is no longer the fastest running index. It's J, the slowest one. So I swapped those indexes. Does it matter? Does it matter how you index the array? Sorry. Make clean. We got 1.5. Let's see what you get now. I put in the sums here to make sure that the numbers are sensible and they are more or less correct. And I got 1.5 with the correct indexing. We should expect it to take slightly longer. With the swapped indexes. Not bad. We are lucky. Most of the time you get slightly longer run times. But then again, the Intel compiler is very, very good. So to illustrate this, we try with a compiler who doesn't recognize. The Intel compiler has built-in heuristics to recognize the matrix multiplication. So if I now say 1 and I say 2000, we'll see that the G-Fortran should give a slightly different, slightly longer runtime, somewhat lower performance. So this is would be a very, very nice commercial one for the Intel compiler. You see, if you swap the indexes using G-Fortran, it takes much longer time. But if you let the Intel compiler build the things for you, it takes almost the same because the Intel compiler has built-in heuristics to recognize these loops, which is interesting.
Which module you have you loaded for this, Ole?
I just relied on the old GCC, the built-in GCC.
Okay.
But it's 12.3, so it's okay. So GCC is always present. So yeah. Well, we'll continue with the Intel compiler. I changed back to iFort here.
So you are not recommending to use a module?
Yes, I would, but it was only for a very short example. So no, generally I strongly suggest you always unload the Intel module and reload the GCC module and swap back again. But it was just a short example to show that the Intel compiler is so smart that it can recognize the loops. So But you could also see that if we built it with the Intel compiler, it will be faster. So we have 21 seconds from, yeah, much longer time with swapping the indexes. So be very careful that the innermost loop uses the first index, which is the important message to take home. So be careful with the indexes. Fortran is column major. And then if you don't pay attention and use the Intel compiler, it actually recognizes these loops. But then matrix multiplication is so much used, so the Intel compiler has built-in routines that recognize these loops and fuse them or use a lot of stuff to help us, preventing us from doing things that have bad performance. So yeah, but the new compiler isn't that good with respect to this. So we get inferior result if we mix up the indexes. So that's this exercise to show that.
So, one question: which Intel module you are using usually? Is the latest one or?
Yeah, this one, 2023A. There are several others.
Yeah, there are these Intel compilers 2023.1.0, something like that.
Yeah, I normally just say Intel.
What is the difference between that two modules? If you say ML Intel.
We can see what's loading now. It loads the Intel compilers, and it's all, yeah, I think that it also loads some more. It also loads the MPI, the MKL, and yeah, a couple of others. So I think the recommendation is to run the whole mod, the simple module. Otherwise but if you have more, if you want more control, you can take the Intel compilers and check whether or not the others are there.
Yeah, for the Intel compiler, there is a module, but it has solely GCC core, zlib, and binutils.
Right, yeah. So like MKL is nice to have. So that's a good thing to have. And also the MPI. So if you use this module Intel 2023A, you get all of this by default with the module. So it's, if I were a dictator of the system, I would say if you load Intel, you would load all the Intel tools. We'll see that later today. So using all the Intel tools would be a nice thing if you launch the Intel module. But as of today, you need to launch some extra modules to get the Intel tools. Right. So we now show that mixing up the indexes could have a performance penalty. The next demo is, yeah, we go to this first. The next one is that non-contiguous arrays have a performance penalties, which is if the arrays are not, all the elements are not back to back, which they normally are. If you declare them like this, allocate this, if you allocate this and this, they are back to back and they are contiguous. So there are no open spaces between the elements, and they are contiguous, numbered from 1 to n in a straight line with no gaps. then this is what you get when you do allocate, and is optimal for performance because you can read the next element in memory is your actual next element. The next memory cell is your next element. So when you fill up a cache line, you fill up all the elements for your vector, and when you need it, it's already in the cache because it was loaded when you load the first cache line. Again, cache is important, and this is the mantra for the whole session, that cache is important. So we can try to run this example. The only difference between this example and the previous ones are that I put the matrix multiplication in the subroutine. That's the only difference. I set n to the size of the first element, or the first column, instead of having extracting it from, if you said just size of x, it will be n times n, but I only need one size of one vector, one column. So I said the first column. It could be any kind of column, but take the first one. Then run it as normal. Then I don't call it here. I start the timer, call the matrix multiplication A, B, and C, stop the timer, show results. Make clean, make MX3. $4,000, we should get some about 1.5 gigaflops per second in 40 seconds runtime. Forty seconds is a very long time, especially if you try to hold your breath for 40 seconds. $1.5, as expected. So now we can challenge a little bit more. We can show what happens if the vectors are not contiguous. I did a little trick here. I wrote another one. The subroutine is exactly the same. It's identical, except that I print out if the vectors are contiguous or not. There is a built-in function that can check for that, since it's very important for performance. You can check it. So I did. I print out whether or not they are contiguous. That one will return T or F, true or false. Then I did a trick. I set an M to twice the N. So I actually declared the matrices twice as big in both dimensions, which is an interesting thing. When I call the matrix multiplication, I took every second element. I said 1 to n, and if you don't say anything, it's going to be the last one, but 2 is every second element. So I take every second element of the vectors. There are 2 dimensions. So this is the first dimension, this is the second dimension. So I take every second element here. So the sizes are the same as before. So same amount of work, but the vectors are not contiguous. So we can see what happened. We don't have to make clean now. We can just say make 4. And it's interesting to see what the Intel compiler does here.
Why did you run MSM3?
Ah, I shouldn't. Good. 4. You see, they come up with true after I've declared them. They come up. They are all contiguous. Of course, they are because they are allocated in the normal way. But when they enter the subroutine, which I declare every second element here, when they arrive here, they are not. FFF, false, false, false. So that should impede the performance slightly. This one took 41 seconds. It's going to be interesting to see how much time it uses when they are not back-to-back. Just to, on the memory bandwidth point of view, it's that if you take every second element, you will fill up the cache line with elements from the memory, but you're only using half of them. So you are actually wasting half the memory bandwidth and half the cache size by doing this. And then it's the question of loading things into the vector unit unaligned. So we get 86 seconds, to twice as long when the wait, which is fairly close to, this is, well, very close to the 2 times that you get from less memory bandwidth. So the penalty is quite severe. So make sure your arrays are back-to-back, contiguous. We can have set some minutes to run the examples for the users, the participants, before we continue. We can go on with them. Yeah, the point is that there is no penalty for putting the subroutine in a module. Yeah. This is the one that we just showed. Notice trick, every second element of the vector or matrix, or yeah. Each of the columns and each of the rows are actually a vector. But then vectors are also used for multidimensional vectors, like if you have 7 dimensions or 4 dimensions or whatever. So it's you use vector for a single one, you use matrix for a 2-dimensional, cube for a 3, but then the 4th dimensional normally repair to an array or vector or whatever. So the language is not really tailor-made for specifying that. Next one that we showed, but then we showed that there was a penalty for non-contiguous arrays when I sent in every second element. Of course, as I said about the difference between C and Fortran, Fortran doesn't really like us to do poor performances. So when I'm so stupid or so mean or whatever you like to call it, that I'm giving vectors that is non-contiguous as parameters to the subroutine, I can force the inner workings of the subroutine to become contiguous. So if I say that the parameters on the subroutine are forced to have to be contiguous, I give them here, I say that this X and Y, they are contiguous. Then the compiler need to copy the data. So the data will be copied and copied back. But if you are doing a lot of computation in the subroutine, that could be very beneficial. And since we are not exhausting the memory here, we are only using 366 megabyte, which is nothing. We can try and see if we get better performance on the number 5. Here you see I put in the keywords. There are X, Y, and Z coming into the subroutine as parameters. I said that they are contiguous. It's a keyword here. As you see in Emacs know the keyword, so it flagged them as keywords. And I forced them to be. We know that they are not contiguous when they arrive, when they are sent here. That we showed the last time, where we got 4 Fs, 3 Fs, FFF, when they arrived inside the subroutine. They are not. Here, I'm forcing them to be so we can see what happened here. Are they continuous or not? So we make the MXM5 and we run it. Yeah, X, yep. My mistake. They are true when they are allocated, but now they are also true here in the subroutine, even though the parameters arriving here are not. They are forced into being continuous, which is the compiler is copying them. And of course, copying is costly, and in both time and space. I mean, especially if the memory is limited, this is not a good option. But if you are writing a subroutine that do a lot of things like we are doing now, then it makes sense to enforce contiguousness of the input vectors or input parameters so that the performance is optimal. Remember, it took 2 times longer. If the vectors, if I said every 4th element or every 8th element, it could be even worse. That's an exercise for you to do, to try out. If you take every 8th element of the input parameters instead of every 2nd, you will have only 1/8 of the memory bandwidth, and you might be in a situation where you have 1/8 of the performance. That's something we can try later on if we have time. So now I get back to the performance I showed at 1.5. That's quite interesting. So if you are writing subroutines, it's a good idea to enforce contiguousness. If the users are so mean and deliberately try to make the world hard for you, and by sending in vectors like I did, they will be enforced in, at least in what you have control of, to be contiguous. Penalty is copying. But that's life. Fortran has a way of helping you to achieve better performance. Non-contiguous arrays are bad in any respect because they upset the cache lines. As we saw, it took 2 times longer. So that's what we learned so far. Cache is important. And you don't have to do very much strange thing to impede performance. Getting maximum performance is not rocket science, but it's important to learn. And testing is even more important. You see, I've printed out seconds and gigaflops. Test, test, and test. Test again, or make script that can run overnight to test. But now we are rapidly approaching 10 o'clock, which I think it's time for a break, Tanya. do you think?
Yeah, we can take a break.
We can see if there are some questions. I don't see any questions, but it will be nice if there are some questions. We can keep open until 10 o'clock.
Yeah.
To see if and do some more explanations.
Probably at the end of this today, I would like to ask this one question. Maybe I can give you the question early.
Yeah,
If
but you can post a question now.
if I get a code from someone else, and if I want to improve performance, what are the methods, tips, and tricks you will recommend?
I'll recommend attending this training, which is it's a bit recursive. I mean, we are in this training, so it's hard to attend this training, but I will try to address the question, but it will all I will address that question.
Yeah.
But as I said repeatedly, I can't teach you how to use brick and mortar and even how many the ratio of cement and sand, but I cannot teach you how to build a cathedral. I can teach you how to build a wall. I cannot teach you how to build a cathedral. Then that's the tricky part, because I can show where the pain points are, but going from there to actually changing the code is hard.
Yeah, I just was thinking that maybe you can point out where should we look.
Yeah, that's the easy part. But if you are unlucky and get codes like Bifrost, where there are no hotspots, it's no part of the code that stands out as the bottleneck. The whole code is a bottleneck. And then you are facing with a major issue. But after this training, you will know how to find the bottlenecks. If there are, excellent. And you could also take the message to take home is that if there is a library, use it, because the library is normally well optimized. So we'll run through some of the tools that we have available today. That's why we spent short time of these simple exercises, because they are not that hard to run themselves, and yeah, we spend more time on some of the tools later on to address that questions. Let's see if there's something on HackMD. No?
Shall we go for a break then?
Yeah, we go for a break.
15 minutes?
Yeah, 15 minutes, and then it's also time to run the tests and the exercises, and 15 minutes, yeah.
Yeah, thanks.
Excellent.
Welcome back. Should we start, Ole?
Yeah, we'll start.
Yeah.
We touched upon compilers, and compilers are different. There are some companies who put more into the compilers than others. The GNU Fortran, while it performs nicely, it's not producing the most optimal code. NV Fortran is NVIDIA. It used to be called Fortran. Then Fortran was too hard, then it was PGI. It changed owners a lot of times over the years, but the core people have always been the same. And after NVIDIA bought PGI, they renamed it to NVIDIA. So now it's called NV Fortran or NVCC and etc. And NVIDIA is putting a lot of effort into this, so they are doing a good job. Intel has been working on this for 20 years or more. Intel software, if it was a separate company, Intel will be the 6th largest software company in the world. But that was some years ago. I'm not sure today, but imagine that they are number 6 in the world of compiler, and they bought a lot of other companies and they put a lot of effort into their compilers. So the Intel compiler is very, very good. It's the best of them. So that's why I normally choose the Intel compiler. It has some issues on the AMD system. You have to pay attention because Intel is trying to prevent us from doing all the nice stuff when using the AMD compilers. Before we go on, I have some examples of flags that we can play with. You can read the manual pages, or you can go to the internet and read the manual in length. And the manuals are generally fairly comprehensive, and there's a lot of interesting things to learn about compilers. So we can try a couple of different compilers. So we can start with the GNU compiler. And of course, all compilers have different flags. So far, I have used -02. We go back to the first matrix multiplication, the simplest one. And we can start with the first type of optimization by saying -03. I wonder if we are up to 13 now. No, it was, I remember the number 3 wrongly. GCC 12.3. Make clean. Make MX1 03. Should put in a default. I didn't. I was lazy. So I suggest that you play with this either paying attention now and record the numbers, maybe a spreadsheet or a simple document or a notebook. Keep it as a reference so you can start doing this on your own code. To see if there is any difference between -02 and -03. There are other tricks you can use to see what kind of code that is generated. Well, you'll see that normally we get 1.5. Now we are up to 1.7. We could. Oh, well, what's happening? Oh, what's happened? Anyway. It was the ad blocker that auto-updated itself. Bummer. Okay, we can put in some more flags. The man page will give you some indications. The processors that we are running support AVX2, Advanced Vector Instructions 2, and Advanced Vector Instructions 512. So they are 512 bits in length. So depending on what kind of precision we are working on, since we are working on 64-bit, 264-bit number is 128, 4 64-bit numbers is 256. So we have 8 64-bit numbers in one register, which in some cases is very good. So we'll see what happened. We have changed the make file, but I haven't, because if I run make again, yeah, good. It's updating regardless. Very good. Now we have compiled our matrix multiplication with 2 additional flags. And we can run and see. Last time it took 36 seconds. With the vector instruction options, it should hopefully be a little bit faster. GNU Fortran is not known for its performant code. It's a good compiler, but it doesn't make the best codes. Yeah, 41 seconds was the one. Yeah. 34 seconds. So we got a little bit better performance, 1.8. So take a note of what we got. I think does it for the GNU compiler. Of course, we could spend the rest of the semester. Well, that's not far. I mean, it's next semester, the spring semester, evaluating compilers, and still we wouldn't be finished. It's a never-ending story. We tried the NV compilers with -03, but we need to module purge, module load, NV. Is that enough? NV HPC. Come on. Yeah, 3. And it also comes with CUDA, but that doesn't matter. We are only using the Fortran compiler. Make clean. Now it's important to make clean because the mod file and the O files from the Fortran module timings, they differ from compiler to compiler. So now we say make MX1. Now we should use the NVIDIA compiler with -03. Yep. And we can try to run it with 4000 again, see what's happened. Are the NV Fortran better than the GNU Fortran, the GNU compiler? Of course, NVIDIA being a company with graphics cards and GPUs and accelerators, they are probably not spending all their effort onto making it perfect for the x86 architecture. They have their own ARM architecture, Grace, which is probably where they are putting most of the efforts, since they are not producing any processors themselves other than the Grace processor, which is ARM. They're not putting all the effort into x86. And we got 39 seconds. Of course, we are not alone on this system, so the load could vary a little bit, but it's not that memory consuming, this one, so it should be fairly representative. If you were concerned with the statistic, you should run this maybe 20 times or something to get an average performance. But we can do better. We can put in some more flags. We can use the flag fast. We can use SIMD 256. We can take prefetch, and we can use unroll. Some of the flag is trial and error. So both O3 and O and fast at the same time might not be the best option. I think O fast also includes -03, so we take that away. We say make MX1 and see what's happening. Should be slightly faster. You could also try SIMD to 512 and see what's happening. But the defaults inside is normally quite okay. Let's see what's happening. It should be faster than 39 seconds. No, not much. Same thing, exactly the same. So the compiler didn't actually benefit from this one. Interesting. So the defaults of the compiler at -03 were actually probably including some of this. But the interesting thing is to try the 256 because the 512, because the processors we are running support 512. We'll see if the compiler does so also. Yes. Could be that we get slightly better. Hard to tell. The 512 registers are power hungry because they are doing so much, so it could overheat the processor, and then the processor, in order to protect itself from being overheated, it clocks down, so it uses less power. The faster it goes, the more energy it uses. It's part of how the inner electronics works. No, 40. So it actually took longer, which we have seen before, because as I said, it could clock down if we overuse the 512. Okay, now you can note down the performance, and then we'll load the Intel compiler. Intel. Right. Make clean. Make MXM1. Ah, it's my mistake. Bummer. Bummer. Sorry for that. Ah, only one. Ah. We'll see how good the Intel compiler is at -03. Five. Only 12 seconds. That's quite interesting. You see now, here is where the Intel compiler shines and outperforms many of the others. Okay, could we do better? Could we tell it to run using a more... We tried the flag called -optimize fast. Then we use the X-Core AVX2. Then we use architecture Skylake 512, and we omit the frame pointer. Frame pointer is a kind of debugging flag that it uses one register. If we get an extra register for the compiler, it generally goes slightly faster because it has one more register to play with, to schedule things on. So we don't have to make clean, we can just say make MX1. I complained it overriding with MR Skylake. It doesn't matter. It works anyway. See if we get better performance this time. We got 12 seconds and 5.3. Wow. Now we get 12.4 gigaflops per second, which is quite interesting. This is as good as it gets. So, lesson learned is that the Intel compiler outperformed the others big time. So, any questions or comments so far?
May I ask a question, Ole?
Yes.
If we don't specify the optimization class 3 or the fast one in our makefile, what is the default?
The defaults are here. Intel has a nice set of defaults. So if you don't say anything, you get decent performance, but not optimum performance. The answer is becoming clear to us in a few seconds now. Because I think the defaults are -02 and a couple of others. It's not Skylake or omit frame pointer and such, and vector, but I think the vectorization is also turned on. We'll see how much time it takes now without anything. Yeah, you see get comparable to the GNU. 1.5.
Yeah.
So you see there's a tremendous difference between using these flags here and nothing. So it's a good idea to have the overriding so we can remove this one. Yeah. So without anything, you get inferior performance. There is no end to how many flags you can try. And some of them are working counterproductive to some others, but generally they are normally additive in performance.
Do we have some man pages for this?
For the compiler?
Flagging options.
Yeah, well, if you go into, I will just I already prepared this. This is the intel.help. If we go down, code generation, which is one of the things I used Core AVX 512, or I said Skylake AVX 512. That's one of them. There are many others, and the Optune, and then we should find the optimization flags. I optimize here. Advanced optimization is a lot of stuff here. Unroll loops. In principle, you can try all of this almost. There's a whole bunch of flags that you can use. Optimization report. That is an interesting one. We can try that because I think we have time to do that. Optimization report.
Yes, I wanted you to show this file. So
Yeah. But we put in optimization report and equals 5 because 5 is okay. It's very verbose, but a small file, small program. So we can see, okay, we have now the optimization report. It's called MX1 opt report. This is an important, but I wasn't sure that we're going to run through this, but this is a really important thing to read. Whole program. Loop begin. So first of all, we have to figure out where we are. The source code. We have to go to this and see. We need to focus on line 43. The line numbers are here. Here. Loop begin. Loop was not vectorized. Inner loop was already vectorized. It's blocked. Interesting enough, it's blocked. It's one of the tricks in the book. Estimate trip count is blocked so that each of the blocks will fit in the cache, and it complains that this one is unaligned access. So that's something that we could work on, to look for unaligned access, but it's a bit hard. And then loop was vectorized, so normally we'll look for loop was vectorized. Compiler has chosen to use XMM or YMM. XMM, and this is in a really internal stuff. The XMM registers are 128-bit registers that can hold two 64-bit numbers, YMM can hold 4 64-bit numbers. They are 256 long. And if you want to force it to use the ZMM, which is the 512-bit vector registers, we can use this flag to override, something that you can play with. So it's also about vectorization. The underline access can be tricky. It's not that's normally when you access over a cache line boundary, which it doesn't like. Then then the problem should be power of 2, but we have asked for 4,000. So this is also something that you can try out. And this is the only time that you get feedback from your actual code. So this report could be quite interesting to read. But going through all of this will take the rest of the semester. So unfortunately, this is something that you have to deal with yourself. But now we've showed how it works. So that brings us from the different compilers over to some other tricks that we can play.
Mm-hmm. Yeah, there is one question on the collaborative
Right.
document.
Yeah. Is the architecture specify a processor specific one? Yes, it is. Would it make sense to change the, yes. Yes, I will point you to a document where I have elaborating quite heavily on this and even how to circumvent the Intel tricks. The Intel asks if the processors are Intel or not. And if it's not, it's complaining. So I have written a document, praise document, that actually show you how to fake this. So yes, the Intel compiler are very usable for AMD processor also, but you need to force it to do what you like it to do. There are a few tricks in the book, and most of them are specified in the report that I'm going to point to later on. But there's also, you can read the man pages of Betsy. Betsy is the biggest system that we have, and the documentation is available on the Sigma 2 website. There's also a few tricks about building code and developing code, which deal with the Intel compiler and AMD processors. So I didn't put it in present mode because we are going so much back and forth. How to explore performance and parameter space. The simplest tool we can do is to record the time. So we say user bin time minus v for verbose, user bin time, because there is a function called time built into the shell that we are not going to use. So you need to specify the path. Right. We should actually be nice to ours. Yeah. Yeah, we have the most performant one because we shortened the wait time. So what's happened here? Command used, user time 5.37 seconds. This is system time. If user time is when the time is spent in running user program, your application. System time is system calls. If that's high, it's generally some sign that you're doing IO or something. Elapsed time is the sum of everything. That is the same that you will have if you are using a stopwatch. It took 5 seconds and 48 hundredths. And you see, I use wall time here, but I take the wall time of not the whole thing. I start the timer here and I stop the timer here. So filling up the vectors or the matrices with random numbers are not counted by me. That's why you get a much higher wall time here than I got here. But this is actually the wall time from the wall time clock here and the wall time clock there, but it's only timing these 3 loops, not print out and random numbers and allocating and so on. So this is the total wall time clock elapsed. Then we can, the maximum resident set size is 366 as I get. This calculates a little bit more. So, okay, this is the maximum resident size. This is very, very important when you ask for amount of memory to Slurm. So if we were to ask Slurm for memory here, we will use the ceiling function and round up to 400. So we will need 400 meg, but this one will actually show you how much you used. So round up to the nearest number, maybe 400, but not anymore, because if you can get away with less memory to Slurm, you might get a faster treatment in the queue, a shorter queue time. So don't ask for more memory than you need. And this is a very nice way of getting hold of that number while you're running. Major page fault requiring IO should be 0, but in this time we got 11. This is not good. It should be as low as possible. Minor page fault is hard to get away with. That's a TLB, table leukocyte buffer cache, which is cache miss there, and it should be low, but it's always a reasonable number. Involuntary context switches, which is we are stopped and started again. It should be very low. Same goes for involuntary. We did some file IO, probably printing out, and the page size was just 4K pages. Exit status 0, so it all went right. It all went okay. So this is the simplest tool that we have in available, is user bin time. Minus V for verbose. You can say all for some A for all, but minus V is a nice one. You get less. You get approximately 1 page of output. So this is the simplest one. We can actually do more. But maybe some users want to try this themselves. We can set aside 5 minutes to play with this tool and see what you get.
Yes.
You have any question, post them while we are playing with software for 5 minutes. I can't find user bin time on my computer on Saga. Are you using the logged in to the C1 use and using this allocation?
You need to log into the compute node.
Yeah, this is the command line. I always expect user bin time to be installed everywhere, but it's not installed everywhere. It's something that some sysadmin has actually to tick off. So yeah, please use the reservation provided, and then you will be on, because we are on later on today. We'll try some accelerated code, and then you have to be on this node. Ah.
You are on C7 node, right, Ole?
Yeah, but the program is not installed on C7 too. It's missing. It's not there. It's only on 721. Interesting.
Okay. Yeah.
Huh. That was news to me. But to file a ticket on that one is pointless, because it will take more than after lunch to somebody to read the ticket, and then yeah. So unfortunately, well, you have to use only try to run the reservation one more, and if you get to schedule on 2, log out and try again. Sooner or later you will be scheduled on 7.1, or unfortunately just follow the demo. Things are not always as we hope to. It's already done. I mean, the walls have ears. So it's already done on 7.2, on 7.2. So try now. I can try. Yes, it's already there. Cool. This is the beauty of having coworkers.
Thanks to Björn Helge.
Yeah. Yeah. He is also coming from the user community, and yeah, and so am I. Most of us here are actually former users. Good. But I think it's time to go on. Now it's going to introduce some of the more cooler stuff. We can load another module, but first I think it doesn't matter. Module list. We have the Intel module, which is fine. Now we're going to introduce some nice tool. The first tool is very easy to use. We load this module. I think it's written here. Module load ARM Forge 2.2.
Before we go further, Ole, just checking if everyone are done with the exercise, or
Yeah, okay, but I thought we had past 5 minutes, so
Yeah.
I assume that it was okay.
Yeah, I didn't see any no, so we can continue. Just
Yeah. So load this module. Then we run the performance report. This is very easy. You just put this in front of your program. It could be an MPI program. It could be anything that you want to profile. X and then 4,000. Perf report. Hopefully it works. Some kind is a license issue. Oh, okay. This is normally a trick. Unset the HPPT proxy. I requested this to be done automatically, but it's not done yet. Maybe I cannot be sure if it's going to be set automatically, unset automatically, but I asked for it. So you have to remember that to unset the proxy. Hopefully it works. Yes. So you could just put in perf report before your MPI run or before starting your executable in the Slurm script, and it will print the report. It will make a report for you. So we go and see what kind of files we've got. The last files are here. You see this one. This is today's date and 10:54, which is exactly now. And we have a report here called a text report. Like this. I also have a printout of it somewhere here. Well, it doesn't matter. I have it on the screen. But the text report is as good as it is. Okay. Command. This should be obvious. One node. Use 377 gigabyte per node of memory. It's a bit too much, right? It should be M. Who cares? Took 26 seconds in the directory, and then the juicy stuff comes here. Summary. It's compute bound in this configuration. All time was spent in computing. There was nothing on MPI because we are not running an MPI program. Is nothing on the IO because we are not doing IO. So this application was compute bound. A breakdown of this time and advice for investigation is further on. No MPI calls. You're right. Okay. CPU code. A breakdown of the 100% CPU time. Scalar operations was only 1.3%, which is very, very good. Vector operations is doing 64% of the time, which is also quite good. Memory accesses was 35%. So 35% of the time that we spent was spent in memory operations. But if we recall, we were running the optimized version of the program. We'll see what happened if we run with only O2 or nothing. Make MX We were quite lucky that most of the time more time was spent in vector operations than memory operations, because that meant that we used the cache fairly good, and that the high performance code that the Intel compiler was able to make did very good use of the cache. So now I'm rerunning. I recompiled with no optimization, where we had the performance comparable to the GNU compiler, and we'll see why it was so slow. Why are the Intel compiler doing so good? So this will take some time. I think it was 80 minutes. No, it was 40 seconds something. But it's also some extra time for the perf report. It's not that intrusive, but it is slightly intrusive. We'll wait and see. We have some time. There, it used 72 seconds. That's over a minute. Quite low performance. So there is it takes slightly longer with the report. Anyway, 1, 3, 5, 7. Text. You see now the picture has changed dramatically. Vector operation only account for 28% of the CPU time, but memory accesses account for 71. So of 71% of the time, that 3/4 of the time that the program was running was spent with memory operations, not doing computation, but just waiting for memory. So that shows us that the cache utilization was very bad, was very low. It's well, bad or good. I mean, it's either high or low. It was very low. So we had a lot of cache misses. So the reason that the Intel compiler is capable of optimizing so much is not the amount of vector operations, because you see the scalar operations are not high either. It is better use of the cache. So the Intel compiler's major benefit here is that it's able to generate code that utilizes the caches better. So by using this tool, we can watch the memory accesses. Of course, we can watch MPI or others, but for now we are only dealing with the CPU bound code. We can study the memory access and see how much better performance we can get on memory access. But for general code, memory access is the bottleneck. And this is quite often the case, that you get 3/4 of the time spent in memory accesses. All scientific programs of a certain size are memory bound, so they spend most of the time in memory accesses. So I urge you to run this tool on your own program. If you do so, remember to unset proxy in the Slurm script, so that you can be able to access the license. So, but it also comes with I thought I had one up here of the HTTP file, but I don't. But there is also a very nice, it's not here. I thought I had it here. No, unfortunately not. It will probably take some time to get the file, but we could try. Here it is. This is the the ARM performance report in web format. It's bright colors and so on, so it's nicer to read. Compute bound. So this is good. 100% of the time was spent doing computation, which should be okay. But then when we start breaking down the CPU time, we see that 81% in this example was spent doing memory accesses. Then the per core performance is memory bound. Use a profiler to identify time-consuming loop and check their cache performance. Okay, that's a direct order, so we better follow it then. We use a text-based profiler. I will use the GNU compiler for this one, and we'll figure out where the code is spending its time. We can put in -03 here to be nice. Or we can actually put in the vector codes also, like this. And then we'll run the, I thought I had profiling. Yeah. We need to module purge, DCC, make clean, and then make MXM1 profile. Okay, what else does it say to do here? We put in the PG, and it actually wants us to have put in this one. We do that too. Not only PG, but also profile. Paste. Right. Then we run the program. Now we should have a report that can tell us where the program spends its time. Of course, we all know then where it is, but if you have a large program, it could be interesting to see if there are functions, procedures, or subroutines, or loops, or blocks that make out a large proportion of our time. And we will see what's happened now. The profiling normally takes a little bit time. Overwriting, yeah, that's fine. Then we need to run this tool here. Paste. Yep, lines executed. Then we can watch here. You see the source code, and we see here 16 million times. Not sure if that's correct, but this is done 64 billion or giga, 10 to the 9th. So this is where the time is spent. This is not that good. It doesn't say any seconds and so on, but it's probably possible to set up. But we'll see that most of the time execution is done in the innermost loop here. 64 billion times is that line executed. So all the times are spent here. So what to do with that? That's the tricky question. That's the cathedral question. What to do now? Maybe this is the point in time where you call for help. So maybe it's time for a little break. So to charge up the brain for the next intellectual step in complexity. What do you think, Tanya?
Shall we have a break until 11:25?
The break is over. So the next issue here is to dive deeper into the cache mysterium or maze or whatever you like to call it. Caches are inherently important for the performance of the microprocessors. A supercomputer is a computer that doesn't need any cache because the memory can keep up with the processor. We have several levels of cache. We have the first level, which is 512 kilobytes, half a megabyte. Second one is 16 megabyte, and the last level is 22 megabytes. And since the smallest amount of memory you can ask for is a whole cache line, then if you ask for a single byte, a whole cache line will be pulled in from memory into the processor. If you only use 1 byte, you will waste 63 bytes of memory bandwidth. Since all programs, or not all, but most of scientific programs are memory bound, we waste a lot if the memory is not properly aligned and contiguous. You see here the C, the matrix C has each of them, of the vectors or the columns or rows are 32 kilobytes because that's 4,000 times 8, 32 kilobytes. And then you see one of these elements are taking one spot in the cache line. Nice. For A, the cache line is filled, which is very good. Since you read in the whole cache line, all the elements in the cache line will be used. But for B, it's worse. Only one of the elements in the cache line will be used, and wasting the rest of the memory bandwidth. On the bottom, I put up the sizes of the caches, and the first cache line can only hold 16 different cache lines. There are other issues in play, but forget those. But assume that size is the only matter, then it can hold 16 cache lines. And since the loops are running at a very high speed, you can easily see that you very rapidly exhaust the cache line, the first level cache with only 16 cache lines. The second one is slightly better. That can contain 524 cache lines. But even that will soon be exhausted. I mean, the loop size is, the vector size is 4,000. And you can only play, plays for 22524. And the last level cache is somewhat better at 722 columns. But still, it's nothing when you are running at a gigahertz speed of the processor. You very, very rapidly exhaust all levels of cache, and you have to fetch data from memory. And then there are the memory, the last level cache, often referred to as level 3, but some computers have level 4 cache, so it last level cache, and level 2 and level 1. So when you request something, it goes through these different cache levels, and the innermost level is the level 1, which is only 0.5 megabyte big, but it has the shortest latency and the highest memory bandwidth. So the point is that data, the closer you get, the better the latency, the shorter the latency, lower the latency, and the higher the bandwidth. So in principle, you should write a program that could fit inside the level 1 cache. But since the level 1 cache is only 0.5 megabyte, you can't. So you have to use the level 2nd level and last level. And if that's not enough either, you have to use the memory, which is very slow compared to the processor. But we stop here, pause here for a little time, and I'll show you a tool that can help you to learn more about your program. We are going to use a profiling tool that help you with, not this way, we'll take the map first. I've already tested it, so we can start the map program. You remember that in order to use the performance report, we had to load the module for ARM Forge to load. So again, we rely that we have launched this module, which I've already done. Module list, ARM Forge, which was the same module as the one for performance report. So you should have noted that down, and it's also in the slides. So we start the map program. During the break, I tested that it works. We get this one up. Remember that if you have been logged in and out, you need to run the unset proxy. You select the executable. You select the argument, which is normally 4,000, and I put up some performance metrics. You can play around with those, but they are the one I have here. You can, different processors have different metrics that you can use. So these are the one that I found that works here. I should probably ask for many more. So we launched the program. See if we can learn something. It's not too hard to use map. It's a very nice program. It counts up here. Then it prints out that it took 12 seconds. It's presenting it. It also required that you have X11 forwarding on, but assume you have that. So what's happened to the first page that we have? We have main thread activity, and that's 100%. We have a CPU floating point that goes up and down. We have memory usage, 535 megabyte. You see here is where it's allocating the memory. Then it uses time to fill up the arrays with the random data, and then it calculates. So then we go here and look for what's going on. 93.1% is spent on here, on this line, on line 46. Executing instruction, 100%. Time spent in instruction executed. 0% is floating point, scalar, very good. 73.5% is spent in vector floating point, excellent. Nothing scalar in integer, vector integer, 0. But the memory access amounts to 40%. So we are only utilizing 40% time 60% of the time, 40% time is spent waiting for memory. And we see this line, we recognize this line from before, so this is easy for us to know. We could have told you that before. But if your program is unknown, you will see that time is spent in a function or some part of the code where you could start thinking of where to optimize. So this will show us where the hotspots are. We could dig deeper into here. We could say CPU instructions, floating point 68%, integer 2.6, memory access 40%, floating point vector 68. We could also dig into an interesting thing. We could say performance counters. You see that the cache misses amount to 6.6 mega events per second, which is quite severe. There are 6.6 million cache misses per second, which is a high number. So it also says here, if you put it on, cache misses. So not too good, but we already know that from looking at the memory access. But the performance report could only tell us that we had memory access, not where they were. Here we actually go into the source code and it can pinpoint exactly where it's happening. So that's part of the thing that you can use map for. This is not the training of a map, it's only show you that it's possible to use map and it can help you pinpointing. So we'll leave it here. We jump straight on to something called the roofline model, which is among the same thing. This is where you have megaflops per second or flops per second, floating point operations per second on the x-axis, on the y-axis. On the x-axis, we have arithmetic intent, which is how many flops per byte, which is how many flops. If you have a number, how many flops are you operating on? So if you are only adding two numbers, this number is 1 or very low. If you are doing a lot of calculations with the number, then the floating point arithmetic intensity becomes higher and you are good. So the bandwidth is here, the peak flops is here. If you are bandwidth bound, you are below this line, and in this area, if you are compute bound, you are above, to the right of this line. Yep, sorry for that. This is what you can plot if you plot it to have memory. That's the roof of memory cap for first level cache, second level cache, third level cache, and memory. So then you will be placed somewhere on this chart if you actually do a plot, make your own plot of your code with the roofline model. You have to read a little bit about the roofline model, but the major point to take home is that you can run this on your own code and see or document that is memory bound. And there is a special tool to do this. It's called the load advisor. I'll show you that. We say just first module purge. Then we say Intel, and then advised. Advisor 23, and then we launch the GUI. The GUI advisor GUI. Take some time for the X11 to launch. An Intel advisor, this is a quite powerful tool, but it only runs through making a roofline model. Otherwise, you'll spend a semester or more just to learn the basics of this one. Ta-da! It's quite a large project. It's quite a large installation. I already have configured the project. I can show you that. You can run this on the command line, but it's nice to show the tools. You see, we have the application here, and then the application parameter is 4000, and the working directory. This you have to set up when you make a new project. And we say, okay, and we press run. They probably complain that we have some older data, but we'll see. If I press run, yeah, it should be running. Wait. It's a large tool that does a lot of things in behind the scenes. So what let's complain about now. Sometimes finalizing, maybe we should have a roofline plot for us now. Pre-compute frequently used data. Here we can easily, first of all, we can see that it found this loop here, and it complains there's a lot of things going on in that loop. So we know already that it was this loop that was the important thing. So if that was your unknown program, you could dig into this one and see that it's here, this loop, that thing's going on. So you have the source code also. But the more interesting things, for me, at least for me, is the fact that we have a roofline model already made for us. We see that the loop comes out at this one, giga integer operations, and for we should have, yeah, anyway, we are, you see, we are below the memory line. So we are actually below this line. And of course, we are below this line. This is the maximum attainable operations, but we shouldn't have integer operation. We should have also floating point operations. Anyway, the important thing is that your program should probably expected to be around here somewhere. So it can make advisor can give you a roofline plot, and you can see where the memory, where your program fits in this, and you will always see some functions and procedures above the memory bandwidth line, which is a good thing because they are operate only in the cache. Because if they are maybe between the memory bandwidth and the memory bandwidth of the cache, you will see that they will be here, and some of them are operating in the second level cache, and they could be here. So this is a very, very important tool to figure out where you are in the memory bandwidth area. We don't have time to dig deep into the advisor tool. There will be a separate training sometime in the advisor tool, but I can show you some other. Here are a pre-run experiment where you can see where we have doing a small one where we are at 25 gigaflops. We are up here, which is in the L2 area, because you see the bandwidth for level 1 cache, bandwidth for level 2 cache, bandwidth for level 3 cache. So we are here. This is quite good. I mean, it's better than being confined by this line here for the memory bandwidth. So it's an example that you could be doing very well since you are running in second level or third level cache. It's another one. You see here at 1 gigaflop, which is not too good, but you see you are confined with the memory bandwidth at 13.34 gigabytes per second. So a roofline plot is always handy to have, especially when you talk to people who want to profile and so on. So recording them, the roofline model and where your program are found itself on the roofline model is always a good thing. Again, one more. So roofline model is important, and it will take, unfortunately, too much time to dig deeper into it, but it is just showing you that it's doable, and you can ask for help about this tool if you want to use it. If you want to learn more how to run this on the MPI applications and so on, this is the two documents this is the document that you could ask. This is the PRAISE Best Practice Guide for Modern Processors and Accelerators. This is the guide for Betsy type system, where I also cover using the roofline model. I cover some of the other Intel tools. I also cover the compiler and the tricks so that you can play to circumvent Intel's tests for genuine Intel processors. So it's all in that guide. It's been well received, so it's quite a good guide, and even though it's a couple of years old, it's all of it still apply. Betsy is still our biggest computer. So take a look on that guide. The advisor we covered. Yep. And now we have a map, but now we are entering a whole new area on the last 40 minutes. It's cheating using accelerators. The nodes that we have been logged into, the C71 and C72, they have NVIDIA. Why am I thrown out? I can put myself back in. Right, I was thrown out for some reason. Okay. First of all, we need to load the correct modules to use the accelerators. But first of all, we'll see that there are some accelerators here. We have 4 of these cards. They are Tesla P100 cards from NVIDIA installed here on C1. There should be the same on C7 too. They have 16 gigabytes. They are sitting on the PCI Express bus, and then Tesla P100. Okay, since they are NVIDIA, of course, we need to launch the NVIDIA software. So we say load NVIDIA. That will make NVIDIA Fortran available. Yes, it is. So we remember the kind of performance we had before. But we can now see that the NVIDIA compiler can do nice things. But before that, we'll introduce this one. This is an interesting part of what the Fortran standard contained. Now we are taking many things because there are trainings for this. So this one, I have links to an NVIDIA training on this one. But in 2008 and expanded in 2018, Fortran introduced something called do concurrent. Concurrent means that they can run in parallel. So it's parallelism built into the language. It's also a C++ variant of this, so with using the ISO standard language. So by introducing, instead of just do j equals 1 to n, we change it to do concurrent j equals 1 to n, mean that in principle, everything inside this loop here could be done in parallel. And there's nothing special, only standard Fortran in this program here. Everything is standard Fortran and going to be there for the foreseeable future. So if you change your program to do, say, do concurrent, it will run in the foreseeable future. So we can now, I've come back to performance because this is just to have best possible performance. And we take a look on the last example we haven't shown yet. This is number 6. It's nothing special. There are a few tricks so that you can play. And the only thing that it's different is the do concurrent. The rest is the same. There's only the outermost loop that is parallelized, do concurrent. We can compile with, first we can compile with multi-core. Mean that we are not using the accelerator, we are using several cores. And I can say MX6C for core. Now we are using the multi-core. So using two cores instead of 1 or more cores. So the first we can do is to set the number of cores to use. 1, MX 6C, I think, yes, and then we run 2000 because it is a shorter wait. Now, 4. It will take us 40 seconds. Take 2000. A single core. You see, this is the number that we are used to, 1.6 gigaflops. So if we use 2 cores, remember we haven't done any special things inside the source code that are not standard Fortran, that will work in any kind of Fortran program. The only thing we did is to replace one loop with do concurrent instead of just do. The only thing we did. And suddenly we have a speed up of 2. We can do better. We can say 4, and we can run. We get quite good speed up just with the do concurrent. If we now say 4 cores and 4000, it will take some more time. Now we are doing only normal multi-core on the CPU. We are just using several CPUs. It took 11 seconds. If we now go to 8, there's a limit of how much this scales on multi-core. If you do plot the scaling, if you plot the number of cores you used versus the performance, you'll see that the scaling isn't perfect, but it's quite good. So now we could use 8 cores and get 7.7 gigaflops of performance using 8 cores, and scaling is reasonably okay. And with just using the do concurrent construct. Here's the do concurrent. But that wasn't the point of this exercise. The point of this exercise was to make use of the NVIDIA cards. So we say make MXM 6 accelerated. Now there is some tricks here. It uses GPU standard instead of having standard parallel multi-core. We say standard parallel GPU, and we ask it to use GPU CC60, which is the Tesla card that we have, the P100. So the code here is multi-core if we are running multi-core, and standard parallel GPU if we are using the GPU. So this is if you are not using the make file, but we use the make file to make it simpler for us. So now I could run 6A at 4000. But before that, I'll challenge you to make a guess. At number 6 or something in the collaborative document, how many gigaflops do we get when we're using the accelerator? Make a guess. And see if somebody come up with a sensible guess. Anything higher than 1.5 would be okay. Well, we could get up to 12 by using the Intel compiler, so it should be more than 12. 20. Excellent. We'll see. We'll see if anybody else Make a guess. 20 is a nice one. I can give you a couple of hints. These cards cost a substantial fraction of a node. They are very expensive. If we could get from 12 to 20 with such an expensive card, would it be worth it? 16. And remember also that matrix multiplication is done only on the card, and they are very powerful. But nice tries for guessing. I mean, you are fairly modest. We'll see if this works. Yeah, you see the numbers. 120. About 120. So you get 120 gigaflops per second by running the matrix multiplication on the NVIDIA card. If I increase the problem to be 2.2 gigabyte, you see it goes up. This is Gustafson's law, that if you scale up the problems, it goes faster. This is a tremendous speed up. And this is the best case scenario also. But if you are lucky and have problems that can benefit from the accelerators, you are very lucky and you are in a good situation. Remember, this is 10 times more than you got from the best performing compilers on a single core. But then again, these systems have 20 cores. So you have to compete with all the cores in the system also. So this is just compared to a single core. So if we were running a large one on 20 cores, you could say that if we set this to, let's say we put this to 16 cores and run the multi-core at 10,000. I'm hoping that I don't exhaust all the memory. So while it looks very nice with this tremendous speed up, remember that if we are comparing to a single core, it's a bit unfair because we have many cores in the node. We have 20 or even more cores. So what you are it's important to compare all the cores with the accelerator. We'll see how long this takes. It's going to take some time. So this is the last thing I wanted to show you, that you can accelerate your Fortran code without using anything else than standard Fortran 2008 and 2018. So when you get on a system where it's a much tighter integration between the accelerators and the processor, you will be very happy to know that you could use the concurrent construct to offload into the accelerator. The time-consuming part is copying data from the main memory of the CPU over to the device over the PCI Express bus, doing the calculation and then copying back. This is a time-consuming process, and with the tighter and tighter integration, that copy process will be smoother and smoother and faster. And sometimes you will use the same memory. So this is something to take along and see what you can do with it. And the Fortran code will run equally well on multi-core than on accelerators. We got, with 16 cores, we only got 17 gigaflops. Of course, we could run at 32. Maybe we'll get some problems. We can say 20. Use all the cores almost in the system. We probably get up, maybe we get up to 20, which is still far away from 121. But be warned, matrix multiplication is very easy for the accelerators to do, and they are tailor-made to do matrix multiplications. They are very good at that. So your normal, climate or weather or a CFD code might not benefit from the accelerator in this kind of extent. But it's worth trying if you have routines or things that could benefit. It might be a good idea to try. But you see, we got up to 21. But I mean, it's a long way from 121 to 21. So even using all the cores, we did not get close to the accelerator. So there is a good reason that the accelerators are so popular, but they are also expensive. So that brings us to the end of the session about performance. And of course, if we had more time, we could spend more time on running the examples yourself, but feel free to run the examples. I mean, we have half an hour and I'm going to be here for the last half an hour, answering questions and helping you to run the exercises. So we could stop the recording if I press record. Dania is back. You have to unmute yourself, Dania.
Yes, I just came back.
Very well. Yeah, you're most welcome.
Then I will stop recording.
Yeah, and we
there were-
open up for questions.
Yeah, just one question I have seen it. What is the energy usage of the accelerator compared to the CPU? Do you have an answer to that, Ole?
The accelerators are very power hungry. So, but you get a lot of stuff done. So while they are power hungry, they also do more work. So it's a hard question to answer. I don't really know the answer. But they are very power hungry. They use hundreds of watts per card. But
Yep.
there's probably a lot of web pages on the internet that can answer that, but I don't really know.
Okay, yeah, we can find some documentation on that. But on that, shall we stop recording and say thank you? And
Yeah,
then take questions?
Yeah.
Okay, and before we stop recording, I just want to say thank you to Ole and thank you to all the participants. We are asking for feedback. Please add your feedback here, and we are planning for a scientific computing course for next year, and we will come back with more stuff for you. And you will get an email. We will record this, we will edit this recording and we will publish it, and you will get an email for the same. So thank you, and I will stop recording and we can go for a Q&As.